Here's something unsettling about space weather forecasts. When officials tell you a solar storm missed Earth, they're technically correct and fundamentally misleading at the same time. February 4th, 2026. Active region 4366 erupts with an X8.1 flare. NOAA runs the numbers, sees the plasma cloud trajectory off axis, and announces the miss. Markets relax. Headlines fade. Everyone moves on. Except the flare's radiation already hit us 8 minutes after it left the sun. The magnetosphere hasn't recovered from January's beating, and that sunspot is holding on to 80% of its magnetic energy while disappearing behind the star. The miss wasn't the end of the story. It was just the intermission. Stay with me, because what's rotating back into view in 2 weeks changes everything we thought we understood about safety. Subscribe and follow along, because this story isn't over. Active region 4366 is still rotating. The magnetosphere is still recovering, and the next 2 weeks will tell us whether the miss was actually safety or just a pause. You'll want to be here when it comes back around. February 4th, 2026. The sun throws a punch, and the world barely flinches. Active region 4366, a sprawling magnetic wound on the sun's surface, erupts with an X8.1 class flare. That's not its first rodeo either. This thing has been going off like a cosmic strobe light, 6 X-class flares in just 10 days. For context, that's like watching a boxer land 6 haymakers in a single round when most fights don't even see one. We're talking about solar cycle 25 peak conditions. The sun doing what it does best at the height of its 11-year tantrum, and this particular sunspot is an overachiever. NOAA's Space Weather Prediction Center runs the numbers, feeds the data into their models, watches the trajectory unfold. The coronal mass ejection, that billion-ton cloud of magnetized plasma that gets hurled into space after a flare like this, appears to be traveling off-axis. Not a direct hit. The modeling shows it sliding past Earth like a fastball just outside the strike zone. The public-facing summaries land within hours. CME missed Earth. Stock markets hold steady. No Carrington event headlines screaming from news feeds. Social media cycles through its 15 seconds of solar anxiety and moves on to whatever controversy is trending that afternoon. Crisis averted, right? Here's what actually happened while everyone was celebrating the miss. The flare itself, that initial burst of electromagnetic radiation, doesn't wait for any coronal mass ejection. It can't. Radiation travels at the speed of light. 8 minutes and 20 seconds after it leaves the sun's surface, it slams into Earth's atmosphere like a photon sledgehammer. X-class flares at this magnitude produce R 3 to R4 level radio blackouts on the day side of the planet. That's NOAA's R-scale classification, and it's not trivial. High-frequency aviation communications go dark. Maritime radio operators lose contact. The ionospheric D layer, that thin shell of ionized particles about 50 to 90 kilometers up, suddenly absorbs radio waves like a sponge soaked in radiation. This all happens before the CME trajectory even matters. Before anyone can say whether the plasma cloud will hit or miss, the electromagnetic punch has already connected. The flare did not miss. It never misses. Light doesn't curve around planets out of courtesy. Now, let's clarify something, because terminology matters, and this is where the public story starts to fracture. When NOAA says a CME missed Earth, they're talking about one very specific thing: the trajectory of the plasma cloud relative to Earth's magnetosphere, that bubble of magnetic field lines that shields us from solar wind, that invisible force field wrapping around our planet like cosmic bubble wrap. A miss means the bulk of that magnetized gas doesn't slam directly into that shield. It grazes us, or it goes wide, or it heads off in some other direction entirely. But here's what a CME miss does not refer to. It doesn't mean the electromagnetic radiation didn't hit. It doesn't mean ionospheric ionization levels stayed calm. It doesn't mean the radiation belts, those zones of trapped particles swirling around Earth in invisible donuts of energy, just shrugged and went about their business. And it absolutely doesn't mean the magnetosphere itself, which has been getting hammered for weeks already, suddenly gets a free pass to reset and relax. Let me take you back to January 2026. Documented G4 level geomagnetic storm. That's major storm territory. Auroras visible at mid-latitudes, which means people in places that never see the northern lights are posting photos like they just witnessed a miracle. Satellite operators are monitoring drag coefficients because when the upper atmosphere heats up and expands during these storms, satellites suddenly encounter more resistance, more friction, and their orbits start to decay faster than expected. Power grid operators are watching voltage fluctuations, monitoring for geomagnetically induced currents that can fry transformers if the conditions align just wrong. That was January. Then comes early February with this flare cluster from active region 4366. 6 X-class events in 10 days, each one pumping energy into the ionosphere, each one rattling the magnetosphere, each one adding stress to a system that hasn't had time to fully recover from the last hit. Systems don't operate episodically. They operate cumulatively. This isn't like getting punched once, recovering, then getting punched again from a neutral state. This is getting punched, staggering, getting punched again while you're still dizzy, then getting punched a third time before you've even regained your balance. The magnetosphere doesn't get a timeout. There's no referee stepping in to give Earth a standing 8 count. So, when you hear CME missed Earth, what you're actually hearing is a compressed summary of a much more complicated situation. The plasma cloud might have gone wide, sure, but the radiation already hit. The ionosphere is already charged. The magnetosphere is already stressed. And the sunspot that launched all of this? It's still there, still active, still magnetically complex in ways that solar physicists are watching very, very carefully. Active region 4366 has a magnetic anomaly, the kind of thing that makes researchers start checking their instruments twice because it doesn't fit the usual pattern. Sunspots are supposed to decay after major flares. The magnetic field configuration should relax. The energy should dissipate. And within days, the whole structure should start falling apart. That's the standard life cycle. Flare, release, decay, done. This one didn't get the memo. There's also the question of timing. Solar rotation means this sunspot is about to disappear from view, sliding around to the far side of the sun where we can't see it directly anymore. The sun rotates roughly every 27 days from our perspective. A little faster at the equator, a little slower at the poles. Active region 4366 is heading for the western limb, that curved edge where sunspots vanish from sight. But here's the thing about the far side. Just because we can't see it doesn't mean it stops existing. And just because a sunspot rotates out of view doesn't mean it stops being dangerous. In fact, some of the most intense solar events in recorded history happened when active regions rotated back into view after spending time on the far side, restructuring, building up magnetic stress in privacy, then coming back around locked and loaded. The mistake wasn't NOAA saying the CME missed. The mistake was the public interpretation that missing meant safety. That we dodged a bullet and everything's fine now. Because the bullet already hit. We're just not bleeding yet. Or maybe we are, and we're not looking at the right places to notice. What if the miss wasn't the danger? What if the real story is what's happening inside the system, in the layers of atmosphere and magnetosphere and radiation belts that most people never think about because they're invisible, intangible, easy to ignore until suddenly they're not? What if the sun already told us everything we need to know, and we're just not listening carefully enough? 6 X-class flares in roughly 10 days. Let me put that in perspective for you. Even near solar maximum, when the sun is at its angriest and most active, that kind of clustering is statistically rare. Most active regions might produce one major flare, maybe two if they're particularly energetic, before the magnetic structure collapses under its own release. The energy gets discharged, the magnetic field lines reconnect in more stable configurations, and the sunspot starts to fade like a bruise healing over time. Active region 4366 apparently didn't read the textbook. After a major flare, you expect to see magnetic relaxation. The tightly wound field lines that were twisted and stressed beyond their breaking point should separate, unwind, settle into less violent arrangements. You expect polarity separation, those regions of opposite magnetic charge moving apart from each other like magnets repelling. You expect rapid weakening within days as the magnetic flux, the total amount of magnetic field threading through the sunspot, drains away into the surrounding solar surface. Instead, what we're seeing is fragmentation without flux collapse. The sunspot is breaking apart visually, sure. It's not one cohesive structure anymore. It's cracking, splintering into smaller fragments like ice under pressure. But here's the weird part. The magnetic flux measurements are still sitting at roughly 80% of the pre-flare peak. The underlying magnetic field strength hasn't collapsed. It's restructured, but it hasn't discharged. Think of it like this. Imagine a frozen lake with deep water underneath. The surface ice starts to crack, splinters spreading across the surface in chaotic patterns. You might look at those cracks and think the ice is breaking up, weakening, about to collapse entirely. But if you measured the water pressure underneath, and it was still at 80% of what it was before the cracks appeared, you'd realize something crucial. The surface is changing, but the underlying force is still there, still intact, still dangerous. That's what's happening with active region 4366. The visible structure is fragmenting, but the magnetic architecture underneath is holding together in ways that sunspots aren't supposed to after discharging this much energy. Now let's talk configuration. This sunspot has what solar physicists call a delta-class magnetic configuration. That's a technical term for a very simple and very dangerous setup. Opposite magnetic polarities, north and south poles if you want to think of it that way, packed tightly together in the same penumbra. Normally, opposite polarities separate across a sunspot group. You get north poles in one cluster, south poles in another cluster, and they're divided by neutral lines where the magnetic field flips direction. It's organized chaos. Delta configurations throw that organization out the window. You get opposite poles crammed together. Magnetic field lines twisted like rubber bands wound too tight, and the whole structure sits there, vibrating with potential energy. It's a powder keg, and what's remarkable here is that even as the sunspot fragmented visually, that delta configuration persisted. The opposite polarities didn't separate and relax the way they should have. They stayed close, stayed tense, stayed primed. Magnetic field measurements from solar observatories confirm this. The flux density, the concentration of magnetic energy per unit area, remained abnormally high even after multiple major flares. That suggests the energy release we witnessed wasn't a full discharge. It was more like a pressure valve opening, just enough to vent some steam, but the boiler underneath is still hot, still pressurized, still capable of building up again. Then comes the far side event, and this is where things get truly interesting. Active region 4366 rotates beyond the western limb of the sun on approximately February 10th, give or take a day depending on differential rotation rates. It slips out of direct view. We can't see it with optical telescopes anymore. We can't measure its magnetic field directly. For all intents and purposes, from the perspective of Earth-facing instruments, it's gone. Within roughly 24 hours of disappearing, we detect an energetic signature, not visually. We can't see the far side of the sun directly, but we have other tools. Helioseismology, for instance. This is acoustic tomography of the sun's interior. Sound waves generated by convection and turbulence inside the sun travel through the solar plasma, and when they encounter magnetic regions, their speed and propagation patterns change. By analyzing these acoustic waves from multiple angles, we can map the presence and strength of active regions on the far side, even though we can't see them. Helioseismology picked up something big, an energetic signature consistent with a major farside event originating from the approximate location where active region 4366 should be. There's also scattered extreme ultraviolet light, faint signals bouncing off the solar corona from the far side, indicating a significant energy release. The magnitude is uncertain because we're not measuring it directly. We're inferring it from secondary signals, like trying to judge the size of an explosion by the echoes bouncing off canyon walls, instead of watching the blast itself. But the signatures are there. Something happened. Something substantial. Now, here's where we need to be careful with speculation, because the data has limits. Far-side magnitude estimates are approximate at best. We don't have direct Earth-facing measurements. We can't say with certainty whether it was an X-class flare, or something smaller, or potentially even something larger. What we can say is that the energy release was significant enough to register clearly on helioseismology and EUV scatter analysis, and it originated from a region that should be calming down, not ramping up. There's historical precedent for this kind of behavior. Recurring active regions in solar cycle 23 showed patterns of magnetic submergence and re-emergence. A sunspot would appear to decay, then rotate to the far side, and the magnetic field structure would actually dive below the visible surface layer, only to pop back up later with renewed complexity. It's like the magnetic field is playing hide and seek with us, ducking underground where we can't track it, then resurfacing when conditions align. Could that be happening here? Possibly. The flux persistence suggests the magnetic structure hasn't fully dissipated. The far side event suggests ongoing activity. The delta configuration suggests instability. Put those together, and you get a scenario where active region 4366 might not be done, not even close. The return window is calculable. Solar rotation is predictable, even accounting for differential rotation at different latitudes. Active region 4366 is at roughly 15 degrees latitude, which means it rotates slightly faster than regions at higher latitudes due to the sun's differential spin. We can project when it should rotate back into Earth-facing view, roughly 27 days from when it disappeared. Late February into early March, depending on how much the differential rotation accelerates or decelerates its specific trajectory. Frame this not as a disappearance, but as an incubation period. The sunspot hasn't gone away. It's gone backstage. And while it's back there, out of sight, it's still doing something. Still restructuring. Still holding on to magnetic energy it should have released. When it comes back around, we'll see what happened during those hidden weeks. We'll see whether the magnetic flux finally decayed, or whether it held steady, or whether it actually intensified. And if it comes back stronger than it left, if it returns with that delta configuration still intact, and that 80% flux retention upgraded to 90 or higher, then we're not watching a sunspot anymore. We're watching a loaded gun slowly rotating back toward Earth. January 19th, 2026, a G4 level geomagnetic storm hammers Earth's magnetosphere with enough force to light up auroras at mid-latitudes. People in states like Iowa and Nebraska, regions that typically never see the northern lights, are standing in their backyards watching green and red curtains ripple across the sky like the atmosphere itself is on fire. It's beautiful. It's also a symptom of something violent happening overhead. G4 storms are major events. They sit just one tier below G5, which is the extreme category reserved for the kind of geomagnetic chaos that threatens to knock out power grids and fry satellites wholesale. At G4, you're seeing widespread voltage control problems in power systems. Satellite surface charging becomes a serious concern because energetic particles are slamming into spacecraft, building up static charges that can arc across sensitive electronics. Spacecraft operations teams are making real-time decisions about which systems to power down to avoid permanent damage. GPS accuracy degrades because the ionosphere is getting hammered with energy, and radio waves passing through it are bending and scattering in unpredictable ways. That was January, 1 month ago. And here's the part that doesn't make headlines because it's slow and technical and doesn't photograph well. The magnetosphere doesn't just snap back to normal after a G4 storm. Recovery takes time, weeks, sometimes longer. Radiation belts, those donut-shaped zones of trapped energetic particles surrounding Earth, often take weeks to fully decay back to baseline levels after a major injection of solar particles. Think of it like a bathtub. You can turn off the faucet, but the water doesn't disappear instantly. It drains, slowly, and if you turn the faucet back on before the tub empties, the water level rises faster than it would starting from empty. Energetic particle populations this solar cycle have been showing slower than expected decline rates. That's not crisis level yet. It's an observational trend, something researchers are tracking carefully, because it suggests the magnetosphere might be retaining energy more efficiently than previous cycles. Whether that's due to specific solar wind conditions, or changes in Earth's magnetic field geometry, or something else entirely, we don't fully understand yet. But the data is consistent. Storms are taking longer to settle. Then comes late April, and this is where things get quietly strange. Solar wind density spikes 20 to 30% above baseline for several days. Not a massive surge, not an obvious CME impact, just a sustained increase in the particle density flowing past Earth. No clearly identified driver. No major solar event that would explain why the solar wind suddenly got thicker. But the effect is real. The magnetopause, that boundary where Earth's magnetic field meets the solar wind and pushes back, gets compressed, squeezed inward. The magnetosphere shrinks slightly under the pressure, and when that happens, the radiation belts and ring current systems inside it respond. They intensify. They get stirred up. Energy that was slowly draining away suddenly gets recirculated, re-energized, pumped back into the system. This is hysteresis, system lag. The tendency of a system to retain a previous state even after the driving force changes. You heat up a material, then remove the heat, and it doesn't cool instantly. It holds on to that thermal energy for a while, radiating it slowly. The magnetosphere does the same thing with particle energy. It gets pumped full of high-energy particles during a storm, and even after the storm passes, those particles don't just vanish. They bounce back and forth along magnetic field lines, drifting around the planet, gradually scattering into the atmosphere over time. If you hit the system again before it finishes draining, you're adding energy on top of energy. You're compounding the effect. There's also been something odd happening with auroral displays. Multiple reports of brighter than expected auroras under what should be moderate solar wind conditions. Conditions that normally produce faint, barely visible auroras are instead lighting up the sky with vibrant greens and reds. That suggests the ionosphere is already in an elevated state, already primed. Like a gun with the hammer cocked back, waiting for even a light trigger pull to fire. This is the preconditioning effect. The magnetosphere and ionosphere form a coupled system, and when one part of that system is stressed, the other responds. If the magnetosphere is still holding elevated particle populations from January's G4 storm, and then you add even moderate solar wind increases in April, the ionosphere reacts more strongly than it would under normal circumstances. The energy input threshold for producing bright auroras drops because the system is already halfway there. Now, let's be very clear about what we're saying and what we're not saying. We're not claiming the magnetosphere is about to collapse, or that we're on the verge of some apocalyptic space weather event. What we're saying is much simpler, and in some ways more concerning. The system is not at baseline. It hasn't been at baseline since January. And every additional input, even moderate ones, is hitting a system that's already elevated, already stressed, already primed to respond more strongly than normal. A CME miss during an elevated baseline is not equivalent to a CME miss during calm conditions. If your magnetosphere is already compressed, already holding excess particle energy, already showing ionospheric irregularities, then even a glancing blow from a solar wind stream can produce disproportionate effects. You don't need a direct hit to cause problems when the target is already bruised. This brings us back to Active Region 4366. 6 X-class flares in 10 days, each one injecting electromagnetic energy into the ionosphere at light speed, each one adding stress to an already primed system. And the CME that supposedly missed, even if the bulk of the plasma cloud went wide, we still got clipped by the edges. We still experienced solar wind density increases. We still saw minor magnetospheric compression. And all of this is happening while the magnetosphere is still recovering from January, while the radiation belts are still slowly draining, while the ionosphere is still showing signs of elevated energy retention. If the magnetosphere is pre-stressed, we need to ask the next logical question. What about the ionosphere itself? Because if the upper layers of Earth's atmosphere are holding charge longer than they should, then we're not just talking about space weather anymore. We're talking about electrical coupling between the atmosphere and the ground. And that's where things start to get really interesting. Let's talk about something you probably haven't thought about since high school physics: a capacitor. Two conductive plates separated by an insulating material, the dielectric. Apply voltage across the plates, and electric charge builds up. One plate gets a surplus of electrons, the other gets a deficit, and the insulating material in between keeps them from shorting out. The charge sits there, stored, ready to discharge the moment you give it a path. Now scale that up to planetary size. The ionosphere is the upper plate, that electrically conductive layer of ionized particles floating 50 to 600 kilometers above your head, constantly being bombarded by solar radiation. The Earth's surface is the lower plate. Conductive ground, oceans, the crust itself. The atmosphere in between, all that neutral gas from the surface up to the ionosphere, acts as the insulating dielectric. It's not a perfect insulator, air conducts a little bit, but it's resistive enough to maintain a voltage difference between the ionosphere and the ground. Thunderstorms maintain this global electric circuit. Every lightning strike is a discharge event, electrons flowing from clouds to ground or vice versa, and collectively, all the thunderstorms happening worldwide at any given moment keep the circuit active. The ionosphere stays charged relative to the ground, typically sitting at a few 100,000 volts positive. Not enough current flow to hurt you. The resistance is too high, but the voltage difference is real and measurable. Here's what we've been observing: extended ionospheric energization after repeated solar flares. The D layer, that lowest ionization region, normally decays pretty quickly after a flare. Electrons recombine with ions. The ionization level drops. Radio communications return to normal within hours. That's the standard pattern. Flare hits. D layer absorbs radio waves. Flare ends. D layer relaxes. Everything goes back to baseline, except the relaxation is taking longer than it should. Ionization persistence beyond the typical decay window. Multiple observatories are reporting this. After the X8.1 flare from Active Region 4366, the D-layer ionization levels stayed elevated for longer than models predicted. Not massively longer, we're talking hours instead of minutes. But in ionospheric physics, that kind of timing difference matters. Why? Because ionization isn't just about radio blackouts. It's about electrical conductivity. A more ionized ionosphere is a more conductive ionosphere, and a more conductive upper plate in our planetary capacitor means the whole system's electrical properties change. There's also the radiation belt particle recycling effect, and this is mainstream physics. Nothing speculative here. Energetic particles trapped in the radiation belts interact with plasma waves in the magnetosphere. Chorus waves and His waves, electromagnetic oscillations that propagate through space plasma, like sound waves through air. These waves can scatter particles out of the radiation belts, sending them cascading down into the ionosphere along magnetic field lines. When they hit the upper atmosphere, they deposit their energy, ionizing more particles, keeping the ionosphere energized, even when there's no active solar flare happening at that moment. It's a feedback loop. Radiation belts feed energy into the ionosphere via wave-particle interactions. Ionosphere stays charged. Magnetosphere stays coupled to the ionospheric conductor. The system maintains an elevated state longer than it would if each component operated independently. Now, carefully framed here because we're entering territory where observational data meets physical speculation. Telluric currents can intensify during geomagnetic disturbances. Telluric currents are electric currents that flow through the Earth's crust. They exist naturally, driven by a combination of solar-wind interactions with the magnetosphere and the global electric circuit maintained by thunderstorms. They're usually weak, barely detectable, except with sensitive instruments. But during geomagnetic storms, they can intensify significantly. The changing magnetic field outside Earth induces electric fields in the conductive ground. And where there's an electric field and a conductor, you get current flow. Power grid operators know this very well. They monitor for geomagnetically induced currents, GICs, which can flow through power transmission lines during storms, saturating transformers, and causing voltage instabilities. The Quebec blackout in 1989 happened because GICs overwhelmed the grid's protective systems. What's less discussed publicly, though well documented in the scientific literature, is that telluric currents don't just flow through human infrastructure. They flow through the crust itself, through conductive rock layers, through mineral deposits, through groundwater. The Earth's crust is not a uniform resistor. It has conductive pathways, weak zones, fault lines where rock is fractured and fluid saturated, and electric current preferentially flows through those pathways the same way water flows through cracks instead of through solid rock. If the ionosphere is staying charged longer than normal, and if the magnetosphere is in an elevated state, then the global electric circuit is running hotter than baseline. More voltage difference between ionosphere and ground. More potential for current flow through telluric pathways. More electrical coupling between the upper atmosphere and the crust. Is this causing anything? We don't know. That's the honest answer. There's no proven causal mechanism linking ionospheric charging to crustal behavior. But the coupling exists. The current flow is real. And we have observational data showing that certain geophysical phenomena correlate with space weather events, even if we can't explain the mechanism. Earlier this year, an AI-assisted space weather forecast underestimated a storm category. Predicted G1 got something closer to G3. Not catastrophic, but notable. Satellite operators had to make adjustments they weren't planning for. Grid operators saw voltage fluctuations they didn't anticipate. The AI model was trained on historical data, learned the patterns, made a prediction based on those patterns, and reality said, no, actually, this time it's different. That's a model boundary issue, not systemic collapse. But it highlights something crucial. Our predictive systems assume stability. They assume the relationships between solar input and terrestrial response are consistent, linear, predictable. They assume the ionosphere responds to flares the way it did during the training period. They assume the magnetosphere recovers on known timescales. They assume the global electric circuit operates within expected parameters. What happens when those assumptions start to thin? When the ionosphere holds charge longer than the model expects? When the magnetosphere doesn't fully reset between storms? When the radiation belts recycle energy more efficiently than previous cycles? The models don't account for hysteresis well. They don't account for preconditioning. They don't account for cumulative stress, because most of the training data comes from periods where storms were isolated events with recovery time in between. But this solar cycle has been different. Clustering, rapid-fire flares, compressed recovery windows. We're operating at the edge of the training envelope, and that's where machine learning systems get nervous. Here's the really interesting part. The layers of Earth's system are not independent. Energy injected into the magnetosphere doesn't stay in the magnetosphere. It couples into the ionosphere via particle precipitation. Energy in the ionosphere doesn't just radiate away. It couples to the global electric circuit. The global electric circuit doesn't exist in isolation. It connects to telluric currents in the crust. It's all one system, connected, coupled, interdependent. Which brings us to a question nobody wants to ask out loud, but everyone's quietly thinking about. What happens when the upper layers remain energized while the crust remains quiet? What happens when energy accumulates in one domain and the timing of release in another domain starts to shift? Since early January 2026, there's been a relative lull in magnitude 6+ earthquakes globally. Not a total absence. Earthquakes never stop. The planet is always moving, always adjusting, always releasing stress along thousands of fault lines simultaneously. But the frequency of major events, the big ones that make news and cause damage, has been lower than the statistical average for this time of year. There was a deep Fiji cluster event, magnitude 6 point something, at over 500 kilometers depth. That's important to note because deep earthquakes and shallow earthquakes are completely different animals. Deep events happen in subducting slabs, oceanic crust, diving down into the mantle, and the physics down there is weird. At those depths and pressures, rock doesn't fracture the way it does near the surface. It undergoes phase transitions, mineral structures collapsing into denser forms, releasing energy in the process. Deep earthquakes can't trigger shallow earthquakes directly because they're mechanically isolated by hundreds of kilometers of ductile mantle material. Shallow earthquakes, the ones happening in the upper 15 to 20 kilometers of crust where rock is cold and brittle and can actually fracture, those are driven by tectonic stress. Plates pushing against each other, pulling apart, sliding past each other. Stress builds up over years, decades, centuries. Friction locks the fault. Stress accumulates. Eventually, the friction fails, the fault slips, and you get an earthquake. That process is overwhelmingly tectonic. Plate motions drive it. No credible scientist argues otherwise. The energy source is gravitational potential energy from plate movement, not solar radiation or magnetic fields or ionospheric currents. But here's where it gets complicated, and this is where we need to tread carefully, because we're entering territory where correlation does not equal causation, but correlation also doesn't equal random chance. There is published research, peer-reviewed, and replicable, showing statistical correlations between certain geophysical phenomena and space weather events. Correlations between geomagnetic storm occurrence and earthquake timing. Correlations between solar flare activity and seismic event clustering. These correlations are small, they're not predictive in any useful way, and they absolutely do not prove causation. But they exist. And when correlations exist without an established mechanism, that usually means one of two things. Either the correlation is spurious, a statistical fluke born from cherry-picking data, or confirmation bias, or there's a real physical connection that we don't understand yet. Mainstream consensus is clear. Tectonic forces are the primary drivers of earthquakes. the energy budget doesn't work otherwise. Solar storms and geomagnetic fluctuations don't inject anywhere near enough energy into the crust to cause a fault to rupture. If a fault wasn't already critically stressed and ready to go, no amount of space weather is going to make it slip. But what if space weather doesn't cause earthquakes? What if it modulates timing? Think about phase transitions in complex systems. These are systems with lots of interacting components, where small changes can sometimes trigger large responses. The classic example is a sand pile. You keep adding grains of sand, one at a time, and most of the time, nothing happens. The pile just gets bigger, but eventually, you add one more grain, and suddenly a whole section of the pile collapses in an avalanche. That single grain didn't cause the avalanche. The pile was already at the critical angle of repose, already primed to fail. The grain just happened to be the trigger. Earthquakes work the same way. Faults build up stress over long timescales. They sit there, locked, accumulating strain energy, getting closer and closer to their failure threshold. Most of the time, they're stable. But as they approach criticality, they become sensitive to perturbations. Small stress changes, tiny nudges in the wrong direction, can be enough to tip them over the edge. Could telluric currents be one of those perturbations? Could electric currents flowing through the crust, intensifying during geomagnetic storms, change the electrochemical properties of fault zone materials, just enough to reduce friction slightly? Could heating effects from those currents, tiny temperature increases in fluid-saturated fault zones, change pore pressure enough to destabilize a critically stressed fault? We don't know. The mechanism is speculative, but the physics isn't impossible. Electrochemical effects in rocks are real. Piezomagnetic and piezoelectric effects, where mechanical stress creates magnetic and electric fields in certain minerals, are well documented. The coupling goes both ways. Stress creates fields, but fields can also create stress, at least in theory. What we do know is that complex systems exhibit increased variance before major transitions. They get jittery. Fluctuations increase. The system oscillates more wildly, even though the average behavior looks stable. And then suddenly, the transition happens. The sand pile collapses. The stock market crashes. The climate regime shifts. Seismic silence does not equal seismic stability in a nonlinear system. Sometimes, quiet is the scariest thing you can observe because it might mean stress is accumulating without releasing. Look at the 2016 Kumamoto earthquake sequence in Japan. Initial magnitude 6.2 event on April 14th. Significant, but not devastating. Then, magnitude 7.0 main shock 28 hours later on a different fault segment. The first event changed the stress distribution in the crust, loaded up adjacent faults, and triggered something much larger. Cascading failure. One fault release altering the stress state of neighboring faults, setting up the next domino to fall. That sequence taught seismologists something important. Earthquake triggering is real. Stress transfer is real. And the timing of events is not random. It's controlled by the state of the crust, the distribution of accumulated stress, and the propagation of stress changes through the fault network. Now, bring that back to our current situation. Magnetosphere stressed since January. Ionosphere holding charge longer than normal. Telluric currents potentially intensified. Active region 4366 rotating back toward Earth-facing view with 80% magnetic flux retention and a history of 6 X-class flares in 10 days. If another major space weather event hits in the next 2 weeks, if the magnetosphere gets hammered again before it fully recovers, if the ionospheric charging intensifies further, if telluric current flows increase, what happens to faults that are already near their failure threshold? We're not saying space weather causes earthquakes. We're asking whether it could modulate the timing of earthquakes that are already going to happen. Whether it could change the when, even if it doesn't change the if. That's a very different question. And it's a question our models aren't equipped to answer, because they assume independence between Earth's layers. They assume solar input affects the magnetosphere and ionosphere, but not the crust. They assume tectonic processes operate in isolation from everything happening overhead. What if those assumptions are wrong? Not wildly wrong, not fundamentally wrong, but wrong enough that edge cases start to leak through the cracks. There's a psychological trap here, and it's one humans fall into constantly. We assume quiet equals safe. No major earthquakes recently means the crust is stable. No major solar storms this week means space weather is calm. No catastrophic failures means the system is fine. But absence of evidence is not evidence of absence. Silence can be stability, or silence can be accumulation. The question we should be asking isn't whether things are quiet. The question is whether things are quiet for the right reasons. If energy accumulates in one domain, atmospheric and magnetospheric, and stress accumulates in another domain, crustal and tectonic, could the timing of release in one influence the timing of release in the other? That's not a claim. It's a question. One that deserves better data and more rigorous investigation. Because the alternative, assuming our models capture everything, might be the most dangerous assumption of all. March 2026, and artificial intelligence confidently tells us to expect a G1 geomagnetic storm. Minor disturbance. Minimal impacts. Power grids will be fine. Satellites will shrug it off. And the only people who care are amateur radio operators and aurora chasers hoping for decent viewing conditions. The forecast is based on solid data. Solar wind measurements from upstream monitoring satellites. Coronal hole structure observed on the Sun. Historical patterns of how similar configurations produced similar outcomes in the past. The AI model ingests all of it, processes the relationships between input variables and output results, runs the probability calculations, and spits out a confident G1 prediction. Nature delivers something closer to G3. Moderate storm conditions. Satellite surface charging becomes a concern again. Power grid operators see voltage irregularities they weren't planning for. GPS accuracy degrades more than expected. Aurora visibility extends several degrees south of where the G1 forecast suggested. Not catastrophic. Nobody died. No transformers blew up. But the prediction was wrong, and wrong in a specific and telling way. The model underestimated the intensity. Let's talk about how machine learning works, in plain language, because this matters. These models don't understand physics. They're not simulating solar wind interactions with Earth's magnetosphere from first principles. They're pattern recognition engines. You feed them historical data, pairs of inputs and outputs, and they learn the statistical relationships between them. When solar wind speed is X and density is Y and magnetic field orientation is Z, the resulting geomagnetic activity tends to be W. The model gets really good at interpolating within the training envelope. If it's seen similar conditions before, it recognizes the pattern and makes an accurate prediction. But machine learning systems struggle catastrophically with out-of-distribution inputs. Conditions that fall outside the range of scenarios they were trained on. Edge cases. Novel configurations. Situations where the underlying relationships might be changing in ways the historical data didn't capture. They fail at the boundaries, not because they're badly designed, but because interpolation and extrapolation are fundamentally different problems. Interpolation is safe. You're connecting known points with smooth curves. Extrapolation is guessing. You're extending those curves into territory you haven't actually observed, hoping the pattern holds, and sometimes it doesn't. This isn't unique to space weather forecasting. Similar AI boundary failures have happened in climate modeling this year. Precipitation predictions that underestimated storm intensity because the atmospheric configuration didn't match historical patterns closely enough. Financial volatility predictions that missed market swings because the combination of factors driving the swing was novel, unprecedented, sitting outside the training data. Systems behave normally until they don't. And AI models trained on normal behavior are exquisitely bad at recognizing when the transition is happening. Now, let's connect this back to active region 4366 and the current situation. 6 X-class flares in roughly 10 days. That clustering pattern is rare, statistically unusual, probably represented in the training data, but not frequently. The model sees it, recognizes it as an outlier, but still tries to fit it into known patterns, because that's what models do. 80% magnetic flux retention after major flare releases, also unusual. Most sunspots decay faster. The historical data probably includes some examples of persistent flux, but not many, and certainly not with this specific configuration and timing. Preconditioned magnetosphere from January's G4 storm with slower than expected radiation belt decay. The model might account for magnetospheric state to some degree, but if the decay rate is anomalous, if the recovery is taking longer than typical historical examples, then the model's assumptions about baseline conditions start to drift away from reality. Stack those anomalies together, and you're building a scenario that increasingly resembles nothing in the training data. Each individual piece might be within known bounds, but the combination is novel. The AI is interpolating between data points that aren't actually representative of the current state. This is where predictive confidence becomes dangerous. The model gives you a number, G1, probability 80%, looks authoritative, looks scientific, and it is scientific in the sense that it's based on data and mathematical relationships. But the confidence interval assumes the current situation resembles the training scenarios. When that assumption breaks down, the prediction becomes unreliable, but the model doesn't necessarily tell you that. It doesn't come with a flashing warning light that says, "Caution, extrapolating beyond validated conditions." You just get the number. And if you're a decision maker, a power grid operator, a satellite mission planner, a telecommunications company coordinating resources, you take that number and plan accordingly. And when the number is wrong, when reality comes in stronger than predicted, you scramble. The March forecast failure wasn't a catastrophic miss, but it was a signal, a canary in the coal mine, an indication that our predictive models, even the fancy AI-assisted ones we're increasingly relying on, might be operating at the edge of their useful range without anyone fully realizing it. The sun may not be escalating. Solar cycle 25 is behaving roughly within expected parameters for a moderately strong cycle. We're near solar maximum. Flares and CMEs are expected. None of this is individually apocalyptic. But our predictive assumptions may be thinning. The relationships we assumed were stable, the patterns we trained our models to recognize, might be shifting in subtle ways. Magnetosphere recovery times lengthening. Ionospheric retention increasing. Radiation belt dynamics changing. Individual active regions persisting longer than typical. Small changes, incremental shifts, nothing dramatic enough to ring alarm bells on its own. But small changes in coupled systems can produce nonlinear outcomes. You nudge one variable slightly, and 3 other variables shift in response, and suddenly the whole system is in a different regime. We built models assuming linear responses, assuming independence, assuming that space weather impacts are transient and isolated. What if the system is more coupled than we thought? What if the impacts are cumulative? What if recovery isn't happening fast enough between events? Then our models are calibrated for a world that no longer fully exists, and the predictions they make are increasingly unreliable at exactly the moments when we need them most. Active Region 4366 is about to rotate back into view. We've got delta configuration persistence, flux retention anomalies, far-side event signatures, and a magnetosphere that hasn't fully reset since January. When it comes back around, the models will try to predict what happens next. They'll look at the sunspot's magnetic configuration, estimate flare probability, calculate CME trajectories if another eruption occurs. But if the sun is doing something our models haven't seen before, if the magnetosphere is responding in ways our training data didn't capture, if the ionosphere is coupling energy differently than historical patterns suggest, then those predictions are going to be guesses wrapped in mathematical precision. And we won't know they're wrong until after reality delivers the answer. Let me tell you about something else that happened in 2026 that has absolutely nothing to do with the sun, but somehow feels weirdly relevant anyway. The discovery of 3 I/Atlas, a newly identified interstellar object tumbling through our solar system. Interstellar objects are rare. We've only confirmed a handful. Oumuamua back in 2017, Borisov in 2019, and now this one. 3 I/Atlas showed up in survey data earlier this year, moving fast, trajectory clearly indicating it originated outside our solar system, not gravitationally bound to the sun. Rapid follow-up observations kicked in immediately. Telescopes worldwide swung toward it. Spectroscopy to determine composition. Photometry to measure brightness and rotation. Infrared observations to estimate temperature and thermal emission. Everything we could throw at it to figure out what this thing actually is before it speeds past and disappears forever. And here's where it gets interesting. Early estimates of composition and mass got revised as new data came in. Optical brightness suggested one thing. Infrared modeling suggested another. The object appeared darker in visible light than its thermal emission implied it should be, which meant either the surface albedo was lower than initial assumptions, or the size estimate was off, or the composition included materials with unusual emissivity properties. Each new dataset refined the picture, but also introduced new questions. Models adjusted in real time. Parameters that were thought to be constrained within narrow ranges suddenly had wider error bars. Theoretical predictions about what interstellar objects should look like collided with observational reality. And reality won, but messily. Why does this matter here? Because it's another example of models adjusting on the fly. Another case where our predictive frameworks, built on limited data and theoretical assumptions, encountered something outside the envelope and had to scramble. Astronomy has gotten incredibly good at discovering things. We've built automated survey systems that scan the sky constantly, flagging anything that moves or changes or appears where nothing was before. Our discovery pipelines are extraordinary. We're finding exoplanets, asteroids, supernova, gamma-ray bursts, transient events of every flavor. But our theoretical frameworks for understanding what we discover haven't kept pace. We're detecting phenomena faster than we can build robust models to explain them. We're living in an era of observational abundance and theoretical lag. Interstellar objects are a perfect example. We have exactly 3 confirmed examples. That's not enough to build a meaningful statistical sample. Every new one we find is a dataset of 1, and if it doesn't match the previous 2, we can't say whether it's an outlier or whether our assumptions about what's typical are just wrong. Same problem with radiation belt dynamics this solar cycle. We've only directly monitored radiation belts with high precision for a few solar cycles. If this cycle behaves differently, if decay rates are slower or particle injection is more efficient, we don't have enough historical data to confidently say whether it's anomalous or whether we just didn't understand the full range of variability. Same problem with ionospheric retention times. If charging is persisting longer than models predict, is that because the models are wrong, or because this particular combination of flare clustering and magnetospheric preconditioning hasn't occurred during our monitoring period before? We're pattern matching machines. Humans and our AI models both, and we need repeated examples to identify patterns. But the universe keeps throwing us single examples of complex phenomena, and we're forced to either overfit our models to limited data or admit that we're guessing. 3. I/Atlas forces that admission. We thought we understood interstellar object properties based on 2 examples. The third one said, actually, maybe not. Let's zoom out and look at the broader context of 2026. Radiation belt irregularities persisting longer than expected. Solar cycle 25. Amplitude exceeding early cycle predictions. Increased detection of high-energy cosmic ray events, though that's likely an instrumentation improvement rather than an actual increase. Far-side solar activity inferred from secondary signatures rather than direct observation. And woven through all of it, this recurring theme: models updating in real time, predictions getting revised, confidence intervals widening, edge cases leaking through. We're not witnessing apocalyptic failures. We're witnessing boundary conditions. The slow realization that our frameworks for prediction, built during relatively stable periods with relatively simple inputs, might not fully capture what happens when multiple systems interact in unusual configurations. Solar physics is bumping into this. We have good models for individual flare events, but clustering behavior and magnetic flux persistence in specific configurations? Less well understood. AI forecasting is bumping into this. Great at predicting outcomes within the training envelope, but out-of-distribution scenarios produce unreliable results, and we don't always know when we've crossed that boundary. Seismology knows this already. We can model stress accumulation on faults, but earthquake triggering and cascading failures in complex fault networks? Mostly empirical, not predictive. And now astronomy, observing interstellar objects and revising models as each new example arrives. Different fields, different phenomena, but the same underlying challenge. Linear models struggling with nonlinear systems. Statistical predictions faltering at the edges. Discovery outpacing understanding. Here's the philosophical synthesis, and this is where everything we've talked about converges into something larger. We've treated Earth's systems as separable. Space weather happens up there. Tectonics happen down here. They're independent. They operate on different energy scales, different time scales, different physical mechanisms. But what if that separation is an artifact of how we study them, not how they actually behave? What if the ionosphere and the crust, the magnetosphere and the fault networks are actually coupled in ways we haven't fully mapped, because we've never had the instrumentation and the computational power to look at the whole system simultaneously? We're starting to get that capability now. Satellite constellations monitoring the magnetosphere in real time. Global seismic networks with unprecedented coverage and sensitivity. AI systems crunching petabytes of data looking for patterns humans can't see. And what we're finding, tentatively, incompletely, is that the boundaries between systems might be more porous than we thought. Energy couples. Information propagates. Perturbations in one domain can influence behavior in another, not through dramatic direct forcing, but through subtle modulation of timing and threshold effects. That's not mysticism. That's just complex systems behaving like complex systems. Feedback loops. Nonlinear responses. Sensitivity to initial conditions. The CME missed. That's true. The plasma cloud trajectory was off-axis, and we didn't take a direct magnetospheric hit, but the flare did not miss. The electromagnetic radiation slammed into the ionosphere at light speed. The magnetosphere was already stressed from January and never fully recovered. The sunspot that launched all this is still magnetically active, still holding 80% flux retention, still exhibiting delta configuration persistence, and it's about to rotate back into Earth-facing view. Meanwhile, seismic activity is anomalously quiet. Telluric currents are potentially intensified. Ionospheric charging is lasting longer than models predict. And our AI forecasting systems just demonstrated they can underestimate storm intensity when conditions drift outside the training envelope. Active Region 4366 already spoke. It launched 6 X-class flares in 10 days. It walked behind the star, and while it was back there, invisible to Earth-facing instruments, It kept talking. Farside signatures suggest ongoing activity. Magnetic flux retention suggests it's not done. When it rotates back around, late February into early March, we're not going to be measuring a single storm. We're going to be measuring a system that's been stressed, primed, energized, and held in an elevated state for weeks without full recovery. A system where multiple domains are interacting in ways our models don't fully capture. A system operating at the edge of our predictive envelope. And if active region 4366 comes back as strong as it left, if it erupts again while the magnetosphere is still vulnerable, while the ionosphere is still charged, while the crust is still quiet in that way that might be accumulation instead of stability, then we're going to find out very quickly whether our assumptions about independence between Earth's layers were correct, or whether we've been modeling separate systems when we should have been modeling one interconnected whole. The sun didn't miss. It just hasn't finished speaking yet, and we might not like what it has to say when it comes back around.